Hello everyone, welcome to the part 1 of tutorial 2. So, let us start with question number 1. Here you are supposed to find out whether the following argument is valid or not. So, you are given some premises and conclusion. So, the first thing that we have to do is we have to convert everything in terms of predicate function. So, we introduce appropriate predicates here. So, of course, the domain is explicitly not given here, but the implicit domain here is the set of students. Okay. So, the first statement here, the premise here is some math majors left the campus for the weekend. So, it is easy to see that this is an existentially quantified statement, it is not making an assertion about all the math majors. But let us first decide what are the predicates that we need here. So, the assertion is about math majors. So, let m of x be the predicate, which is true if the student x is a math major, and we are saying something regarding whether he has left the campus for the weekend or not. So, that is the second property for the subject x. So, that is why I introduce a predicate w of x, which is true if the subject x or if the student x has left for the weekend. And I am making a statement that there is some student x for which both these conditions are true. So, that is why this is an existentially quantified statement with conjunction inside. The second statement here or the premise here is that all seniors left the campus for the weekend. So, this is a universally quantified statement, and if you see clearly or closely here, the interpretation of this statement is that if a student x is senior, then he has left the campus. So, there is an implicit implication here, and that is why this premise can be represented as for all x, s of x implies w of x. The conclusion that I am making here is some seniors, so that means an existentially quantified statement, are math majors. That means at least one student is there for which the property that he is a math major as well as he is a senior are true. Now, we have to verify whether this is a valid argument, and as per the definition it will be a valid argument if based on the premises I can draw the conclusion for every possible domain. However, it turns out that this is not a valid argument, and we can give a counter example. You can give multiple counter examples here. Even if you show one counter example, that is sufficient to show that this argument form is not valid. So, the domain that I consider is the following. Imagine you have a college where you have 3 students x1, x2, x3, and say with respect to those 3 students the status of the 3 predicate functions are as follows. For x1 the property m is true, w is true, but s is false. Student x2 the property m is true, the property m is false, the property w is true, and the property s is true, and so on. Now, you can verify that with respect to this domain and this assignment, the premises are true. Indeed, there exists a student for which the property that he is a math major and he has left for the weekend, he has left a campus for the weekend are both true, namely x1 is one such student. And similarly, the second premise, namely all seniors have left for the campus, is also true. So, who are the seniors here? The seniors are x2 and x3, and indeed x2 has left the campus and x3 has also left the campus. So, both your premises are true, but what about the conclusion? Is there any student who is a math major as well as senior? Well, it turns out the answer is no. That means my premises are true here, but my conclusion is false, and that is why this is an invalid argument. Let us see question number 2. In this question you are given two predicates which are defined for you. I of x denotes that a stamp collector has stamp x in her collection, and f of x y denotes that stamp x is issued by country y, and you have to express the statement that this collector has exactly one stamp issued by each African country. So, I am making a statement about a specific collector, and I want to state that for each African country he has exactly one stamp issued by that country in her collection. So, of course, my domain here set of all African countries, right. So, if you recall from the lecture, whenever we face this scenario where we want to represent that a property P is true for exactly one element of the domain, then there are two things which we have to represent. The first thing, that the property is true for at least one element of the domain. In this case, the property is that for every African country there is one stamp at least issued by that country which is there in the collection of the collector. That is first part here, which is represented by this expression. So, this expression means that for every African country Y, there is at least one stamp X such that the stamp X was issued by that country Y and the collector has that stamp X. For the moment, forget about what is there in the remaining part of the expression, forget it, just focus on this part of the expression. But this is not what we want to represent, because I can't stop with this expression, because this expression also means that there might be multiple X values for the same Y, for the same country Y, where those other X stamps are also issued by the same country Y and the collector has those other X stamps in her collection. That is not what we want to represent. We want to represent that exactly one value of X or one stamp X is there for each country Y. So, that is why we have to put this second part of the expression. For the moment, forget about this negation and whatever is there before the conjunction, forget about that as well. The second part of the expression denotes that there can be other stamps X prime issued by the same country Y and which is also there in the collection of the collector. And you see, I have very carefully put the parenthesis here. The scope of this Y is still covered by this for all Y. Okay. The scope of this universal quantification is carried over to this Y as well. Okay. And the scope of this X prime, this X prime is again within, it is a nested quantification here, this there exists X prime, it is a nested quantification falling within this for all Y. Okay. So, the second part of the expression denotes that there might be other stamps X prime issued by the same country Y which can be there in the collection of the collector. But I do not want that to happen, that is not what I want to represent. So, that is why I put a negation here, and if I put a negation, that means there can't be any other stamp X prime different from X which is also there in the collection of the collector and X prime was issued by the African country Y. And that is why the conjunction of these two things represents the required statement. Of course, you can simplify this, apply De Morgan's law and take this negation inside, convert everything, make everything in the form of an implication and so on, that also you can do. But even if you write this expression, that is correct. Part A of question 3 asks you to do the following. It asks you to give an example of a predicate P of n over the domain of non-negative integers such that the proposition P of 0 is true, but the universal quantification for all n P of n implies P of n plus 1 is false. So, if you want to make P of n implies P of n plus 1 to be false for all n, that does not mean you have to make it false for every value of n in the domain. Remember, the meaning of this universal quantification is that it will be true for all, the universal quantification will be true if it is true for every value of n in the domain. But even if it is true false for one value of n in the domain, that shows that this universal quantification is false. So, here there can be multiple examples of such a predicate P. A very simple example is the following. Say my property P is that integer n is even. When I substitute n equal to 0, the resultant proposition is that 0 is an even integer, which is a true proposition. But what about the statement p of 0 implies p of 1? It is false, because p of 0 is if n is even, if 0 is even, implies 1 is odd, which is clearly a false implication, and that means since p of 0 implies p of 1 is false, for all n p of n implies p of n plus 1 is automatically false. Okay. It does not matter that p of 1 implies p of 2, this is true, right, because p of 1 is false and p of 2 is true, false implies true is true, whereas p 2 implies p of 3 is false, and so on. Okay. So, I have a statement here which is for which this universal implication is not coming out to be true for every value of n in the domain, and that is why this is an example of such a predicate. The part B of the question is just an opposite of part A. Here you are asked to give a predicate q such that q of 0 is false, but the universal implication q of n implies q of n plus 1 is true. So, now my example here is that property q of n is defined that integer n is positive. It turns out that q of 0 is false, because q of 0 is the proposition that 0 is positive, and definitely 0 is not positive. So, this proposition is false, but it turns out that q of 0 implies q of 1 is true, because q of 0 is false. So, false implies anything is true, and now any statement of the form q of n implies q of n plus 1, everything will be true. That means, now I can say that this universal quantification is true. Okay. Now, let us see question number 4. Here I have to show, or I have to either prove or disprove that the left hand side expression implies the right hand side expression. So, you see the left hand side expression, I have explicitly added the parenthesis here. So, the x within the p and x within the q are different here, whereas in the right hand side the x both within p and q are same, because both of them are covered by the same there exist, whereas in the left hand side the first x is covered by the first there exist and the second x is covered by the second there exist. The informal way to interpret this statement is, if you are given that property p is true for some element in the domain, and if you are given that property q is true for some element of the domain, then can you conclude that both p and q property are true for some element of the domain? And this need not be true. I can give you a very simple counter example. Imagine a domain where you have two values of x possible, and say property p is true for x1 but false for x2, whereas q is false for x1 and true for x2. In this case, you can check that your left hand side is true, because indeed the property p is for at least one value of the domain, and indeed the property q is true for at least one value of the domain, but that does not mean that it is the same x for which both p and q are true. Individually p might be true for some x and q might be true for a different x. That does not mean there exists an x for which both p and q property are true, and which is happening in this case. So, this is not a correct statement. What about the part B is the implication in the reverse direction. It says that if you are given that there exists some x value in the domain for which both property p and property q are true, then you can conclude that individually the property p and q are true for some value in the domain. So, we can prove this, and the way we prove this is as follows. So, since you are given LHS, so to prove that this implication is true, we have to show that if I assume left hand side is true, then I have to show that the right hand side is also true, because for all other cases an implication always turns out to be true. That means, my false implies anything is true, and so on. So, assume your left hand side is true, that means there exists some x value in the domain for which both property p and q are true. I do not know the exact value of that x because my domain could be very large, but I can say that that element x for which the left hand side is true can be represented by C. So, this is your existential instantiation. Okay. So, I know that proposition P of C is true as well as the proposition Q of C is true. I stress the value of C is not known here, it is an arbitrary element, but it exists. Now, since the conjunction of the two propositions P of C and Q of C is given to be true, this is possible only if the individual propositions P of C and Q of C are true. And if the proposition P of C is true, that means I can say that the existential quantification there exists P of x is true, and in the same way, since the proposition Q of C is true, I can say that the existential quantification there exists Q of x is true. Both of them are true, that means the right hand side is true. That means assuming left hand side to be true, I can conclude the right hand side is true, and hence this identity is a correct identity. The fifth question is a very interesting question. It asks you to show that there are infinitely many prime numbers, and there are several interesting proofs possible for this statement. Let me show one of them. So, I am trying here a proof by contradiction. So, the statement I want to prove is there are infinitely many primes, but I assume a contradictory statement that there are only finite number of primes, say n number of primes, n could be anything, it could be 2, 3, 4, anything. Now, what I do is I define a new number which is the product of my finite number of primes which I am assuming to exist plus 1. Now, what can I say about the number q? There can be two possible cases. So, now I apply the proof by cases here. My q could be a prime number itself, my q could be a composite number, and there can't be any third case possible with respect to q. It turns out that if q is a prime number, then definitely q is different from all your numbers, prime numbers p1, p2, pn that are the only prime numbers you assumed to exist. That means, now you have found a new prime number. That means, your listing of p1 to pn is not an exhaustive listing of all the prime numbers that exist, right. So, you got a contradiction, whereas it might be possible that q is a composite number. Now, if q is a composite number, I can show that none of these prime numbers p1, p2, pn will be a factor of q, none of them will divide q. Okay. On contrary, assume say for instance p1 divides your number q. Now, if p1 divides q, that means p1 is a factor of q, then we know that p1 is a factor of the product of p1 to pn, because that has p1 in it. So, that means you have now a number p1, a prime number p1, which divides both q as well as the product of p1 to pn. That means, it will divide the difference of q and the product of p1 to pn, but the difference of q and the product of p1 to pn is 1. That means, p1 divides 1, but that is not possible because p1 is at least 2, because you are assuming that p1 to pn are primes and the smallest prime that is possible is 2, and 2 can't divide 1, right. That means, we have shown here that p1 cannot divide your number q. In the same way, we can show that p2 does not divide q. In the same way, we can show that pi also does not divide q. And in the same way, I can show that pn does not divide q. But q definitely has a prime factor, because that comes from my fundamental theorem of arithmetic. You take any number, it can be expressed as product of prime powers. That means, it has definitely one prime factor, say p, but at the same time I am showing that that p cannot be p1, it cannot be p2, it cannot be pn. That again shows that I am missing a prime number p in my listing of prime number. That means, my list of prime numbers p1 to pn, which I assumed, is not the complete list. So, that is a contradiction I get in case 2, right. It turns out that very often students just give the following argument, which is an incorrect argument. They say that for surety, since q1 is not divisible by p1, since q is not divisible by p1, q is not divisible by p2, q is not divisible by pn, they end up with the conclusion that q is definitely prime. That is not correct. Let me demonstrate that. Imagine that these are the only prime numbers which you assume to exist. Now, your q in this case will be the product of all these prime numbers plus 1, and as per your argument, q should be always prime, because it is not divisible by 2, it is not divisible by 3, it is not divisible by 5, not divisible by 7, not divisible by 11 and 13, but it turns out that q is composite here, where the prime factors of this composite q are 59 and 509, and these are the two primes which are not there, which are missing from your list of exhaustive prime numbers, which you are assuming to exist. And that is why in case 2, we can't simply stop with the argument that q is also a new prime number, which I am finding, because it is not divisible by p1, p2, pn. The correct argument is, we will show that q will have at least one prime factor which is not present in the list of prime numbers which I am assuming to exist, which is demonstrated by this example. Now, let us see question number 6 and 7 together. We will first see question number 6, and the solution of question 6 will be used for question number 7. The question 6 is, you have to prove that there exists at least one real number among a set of n real numbers which is greater than or equal to its average, their average. Okay. I stress here that a1 to an are arbitrary here. You can't show concrete values of a1 to an and prove this statement for those concrete values and conclude that this statement is true. This is a universally quantified statement. So, how do we prove it? We have to take arbitrary values of a1 to an and prove the statement with respect to those arbitrarily chosen values of a1 to an. What we do here is, we give a proof by contradiction. So, our goal is to prove that the average of a1 to an is less than or equal to some ai, but instead I assume that each of the individual numbers among these n numbers is less than their average. That means, the first number is less than their average, the second number is less than the average of the n numbers, and similarly the last number is less than the average of the n numbers, right. That is a contradiction. Now, if I add these n equations, I get this inequality, and if I substitute the value of the average by this formula, I come to the conclusion that the summation of n numbers is less than the summation of n numbers, which is not possible, which is a contradiction. That means, assuming this contradiction leads to a false conclusion, that means the statement is a true statement. That means, you take any n real numbers, any n arbitrary real numbers, they could be positive, negative, they may be same, different, at least one of them will be greater than or equal to their average. Now, based on this, I want to solve question 7. In question 7, you are given the following. You are given the numbers 1 to 10, which are placed around a circle in any arbitrary order, maybe in ascending order, descending order, maybe the odd numbers first, even numbers next, and so on. So, the order is not given, it is an arbitrary order. Then the question says that it does not matter in what order you arrange the numbers 1 to 10, there always exist 3 integers in that arrangement, which will be in consecutive locations such that the sum of those 3 numbers will be greater than equal to 70. Okay. So, I stress here this is with respect to any arbitrary arrangement of the numbers 1 to 10. So, pictorially you can imagine that you are given this arbitrary circular ordering of 1 to 10, where a 1 can be any number from 1 to 10, a 2 could be any number from 1 to 10 and so on. I have to show that once I freeze this arbitrary ordering, in this arbitrary ordering there exists a collection of 3 integers in 3 locations such that their sum is greater than equal to 70. And I want to take the help of question number 6, whatever I have proved in question number 6. So, what I do here is, since the question involves sum of 3 numbers, what I do here is, once I freeze this circular arrangement of 1 to 10, I take the following sums. I take the sum of first 3 numbers, namely a 1, a 2, a 3, that is my S 1. In the same way, I take the next sum of the sum of next 3 numbers, namely a 2, a 3, a 4, I call it S 2. I take the sum of a 3, a 4, a 5, that I call it as S 3, and in the same way I take the sum of a 10, a 1, a 2, that will be my last sum, namely S 10. Okay. And what is my goal? The question says that either S 1 is greater than equal to 17 or S 2 is greater than equal to 17 or some S I is greater than equal to 17. That is what I want to prove here, because I have taken the different possible sum of 3 consecutive numbers in this circular arrangement. Now, what I can do here is I can interpret S 1, S 2 up to S 10 as 10 possible values, right. That means, let n equal to 10. Now, what will be the average of these sums S 1, S 2, S 10? It does not matter what are the values in your circular arrangement. If you take the average of these 10 sum values, then in the denominator you will have 10, because n is 10. But when you take the sum of S 1 up to S 10, each number in this arrangement will occur 3 times, okay, because a 1 will be occurring in S 1, a 1 will be occurring in S 10 and a 1 will be also occurring in S 9. In the same way, a 2 will be occurring in S 2, it will be occurring in S 3 and S 4, okay, and so on. So, each of these values a 1 to a 10 will be occurring thrice when you take the average, and when taking the average you will be adding S 1 to S 10. And if my claim here is, if you add S 1 to S 10, each of these values a 1 to a 10 will be occurring thrice, and the possible values of a 1 to a 10, each of them belongs to 1 to 10 and only once they occur. That means, I know that if you add the values a 1 to a 10, you are basically adding the numbers 1 to 10, and the summation of the numbers 1 to 10 is nothing but 55. That means, I know that it does not matter in what order the numbers are arranged. If I define sums like this and take their average, it will be 16.5. And from previous question, I know that either S 1 is greater than equal to the average of S 1 to S 10 or S 2 is greater than equal to the average of S 1 to S 10 and so on. That means, at least one S I is there which is greater than equal to 16.5, and each S I is an integer, because S 1 is the summation of 3 integers, S 2 is the summation of 3 integers, in the same way S 10 is the summation of 3 integers. So, each S I is an integer. So, what is the smallest integer which is greater than equal to 16.5? Well, it is 17. So, that shows that either S 1 is greater than equal to 17, S 1 is equal to 17 or S 2 is 17 and so on. Okay. So, that proves solves your question number 7. Thank you.